It's literally at the top. All right. Yeah, perfect. Okay. So let's see. With that, I'm going to jump into 3D Vision Part 2, for which Val and I have decided we love nerfs the most. So we're just going to cover nerfs today. If you want, we did make a couple of slides on like monocular depth estimation if you want to come up and like check those out afterwards. But today it's really, we're just going to be talking all about nerfs because they make me happy. So yeah, so we recapped nerfs a little bit. The basic idea, again, you have a black box function that takes in your position in space, X, Y, Z, and is going to output your color, your density. And if we want to figure out what an object looks like from a given perspective, we're going to query going out from our camera, from our current location, and ask our black box function, what is the color, what is the density at all these points, and try and from that sort of figure out what is this image actually going to look like. And that process is called rendering. That is the basic idea of what a radiance field is. And the recap of volume rendering: color is the weighted average of all the samples that we take as we go out along the rays. Your visibility is proportional to the density, and inversely proportional to the amount of stuff in front of us. So if we have lots of stuff in front of us, like for the bulldozer, after we've passed through the bulldozer, there's lots of stuff that was in front of it, particularly right here, where the actual object was. So even if this point right here returns a really big density, even if this point here past the bulldozer returns a really big density, because there's a ton of stuff in front of it, we're still going to weight it super with a very small value. And you can see sort of the intuition of this on the right-hand side. This is not particularly color friendly. The top is supposed to be brown, the bottom is supposed to be yellow, or I'm sorry, orange. So you can imagine casting out a ray in a scene, and it passes through. In the first, it's just going to pass through a brown object. As we sample along this ray, the density that we observe is going to be very little, and then it's going to spike when we're passing through the object, and then the density is going to be very little again. So we only really pass through one just brown object. So the color we're going to return is going to be brown. And when we actually learn the radiance field, we're going to compare it to our ground truth image of this object and say, like, okay, how does the color that we came up with using our function compare to the real color? And then in the second example, just to hammer this point home, that it's really only the closest thing to you that contributes to color. We can imagine two objects in the scene. The first one will be orange, and the second one will be yellow. We have a ray that goes through it. Both of these objects. We're going to sample a whole bunch, right? The first thing we come into contact with is this orange ball. And you can see the density spikes at the orange ball, and then goes down again when we're in between, and then spikes again when we hit the yellow ball. The color we're going to return will be orange, because all that matters is the color at this location here where the spike first hit. So like, sure, we do hit a yellow ball eventually, but in this case, it is behind the orange ball. So the color we get back is just orange. So yeah. Do people have more questions on this intuition, or yes? Yes, first, sorry, his hand is raised.
The density of like the first spike is lower than the density of the second spike.
Yeah, it's gonna, because the density, it's the first, if the first object you come into contact with is like glass and it's not perfectly dense, you're gonna get some contributions of color from that. Maybe you'll get like a weight of like 1/2, and then the object behind it that's super dense is probably going to contribute to the rest of your color. But because even though it's perfectly dense, it's 100% dense, because it's behind something else, it's only going to get a weight of like maybe 1/2. Yeah. Say that again. Oh, refraction. Yeah, we'll talk about that a little bit, how we handle like reflections and stuff like that. Yeah, that's a really good question. We're going to talk about that in a little bit. Yeah, what's up?
So with the value of T, that was measuring like how far you are in the object, like sitting in front of it.
Yes.
So personally,
Mhm.
if you just did like a basic like density times color, right? Like we can see like an average of those two peaks. Like you're saying that you want to weight for peak.
Yeah, we want to weight it more.
Like how's that?
So basically what we're going to do is we have the densities, say, okay, say we're sampling the yellow object here. Can you all see this okay-ish, hopefully? Okay, so say we're sampling the yellow object here. First thing we're going to do is we're going to get the density, like sigma. In this case, it's written beta. Beta is it's a proxy for just sigma. So I'm just going to write sigma for now. So we get sigma I right here. And we're also going to come up with T. So how do we get T? What we're going to do is we're basically going to sum all the density along here. We're going to sum it all up, add up all the density, and then take 1 over the sum of all of our densities accumulated up until here. So if there's a lot of stuff right here, Ti rather, if there's a lot of stuff right here, if our densities in front of us are really big, that makes this value T super small. So T is really big when there's not much stuff in front of us. T is super small when there's like other stuff in front of us, basically. And you're going to do that by just summing up all the density that came before us along our array. Does that make sense? Okay, party on. Any more questions? All right, party on. So that is the intuition. Whatever we hit first is going to be weighted heavily. Whatever we hit later on, not as important. So what is the goal of neural radiance fields? The basic problem is we have a lot of different images of an object. Like I just walked around an object, took a video, and then I look at all the individual images that make up that video. And I want to say, okay, given all of these images, how can I come up with a neural radiance field that's going to be able to generate new views of this object? That's basically the problem statement. Come up with a neural radiance field so we can query at points in the scene and come up with new images too. How do people feel about that? Yes, friend?
How hard is it to get the ground truth positions and directions?
Yeah.
Because I've seen videos of you guys like
Yeah.
going around.
It's pretty non-trivial that we can find all the positions of all of these, you know, where the phone travels as it's moving through space. There's some programs you can run that'll basically like if you have an object with really sharp corners, it'll kind of look at the position of all the corners as we move and sort of triangulate. I'm not going to go into it too much. It's the basic problem is like called structure from motion. Like, how do we figure out, given like a video of like us moving around an object, how do we determine like some key points along that on that object? There's programs that do it like Colmap. It's really gross to run. It's questionable whether or not this is cheating using these positions to begin with. Yeah, it's a very difficult problem. Classes like 194.26 cover that. Classes like 280, CS 194.26, CS 280. It's definitely non-trivial, but for the sake of this problem, we're just going to assume that they're given and they're like pretty good.
In your experience, that's a big obstacle.
It's really obnoxious to get it, but it's doable. And honestly, I still feel like it's kind of cheating to have that to begin with. But there's some derivations of this that don't necessarily require this. If you just have a continuous video, yeah, it's a real problem, but it's doable, and it's for the most part pretty accurate. It's like a classical technique that was long before the era of deep neural networks, so it's been around for a while. Yeah, good question. Are there more questions before I keep going? Yeah, what's up, Beyond?
So just like when you, that's what I assume, like when you render like the videos like or so when you're
Yeah.
that you're stringing together, like you're generating a single frame.
Yep. One frame at a time. Yeah, basically that's what it is. We're just gonna
the way you guys like like you assign the camera angles you're starting.
Yeah, exactly. Yeah, when we have our image, we're gonna say, okay, like if we want to generate a video of a camera like moving around like this,
Yeah.
we're just going to figure out where all the cameras are, sort of in like a little circle out here. Just take a bunch of those views along that circle, generate images together, and then yeah, just play them really fast, and then we get the video. Yeah, what's up?
But we have like a second camera where it's out in the specs and like, you know the position that he's not gonna attack position on the second camera. For the first camera.
I mean, technically, with your first camera, you can just assign it to the origin. Like if we're taking a video and like moving it around, like our coordinate frame is whatever we want it to be. Like this object is still the exact, my laptop is still my laptop if I rotate it a little bit, or if I assign my axes to be rotated a little bit, it's still the same thing. So with your first camera, you can technically just call it the origin. Does that get at your question at all?
Maybe I'm some time.
Okay. Yeah.
Camera slowly figure out where the second camera is. Or does that?
It reminds me a little bit of like SLAM, like some people simultaneous localization and mapping. It's sort of like self-driving. Like if you have a continuous video of your car moving along, how do you figure out where stuff is and where you are? And in that problem, yeah, you do definitely take advantage of the fact that your second frame is going to be pretty close to wherever your first frame in your video is, and just try and figure out like, okay, like how much did we move in this little one gap from our first frame? Does that kind of get at it a little bit? Okay. Are there more questions? All right. Yeah. So whether or not it's cheating, it still gives cool results. So we're gonna run with it. And the paradigm is we have lots of images of a scene. And we have lots of images of a scene. We want to just figure out, okay, from these, can we learn a neural radiance field? And then that would allow us to render new views if our neural radiance field is really good. So yeah, so like why do we bother with 3D at all? Because it seems like, I mean, this is deep learning after all. Why don't we just train a network that just takes in all of these different images? Oh, come here. That just takes in all of these different images and just outputs a new image. If you just say, okay, here are all of our cameras. Here are the locations where all these images were taken from. Here are our images. Predict an image given a new camera position that we're going to give you. Like, why do we bother putting it through this bottleneck of like learning a neural radiance field at all? That's sort of a pretty non-trivial question. Like, oh, come here. Come on, dude. What's going on? Oh, I'm on the wrong slide deck. That's cool. Okay. So why do we bother with this bottleneck? Why do we bother learning a neural radiance field instead of just telling a neural network like, hey, give me a new view of this object from this new position? And the basic answer is like shape consistency, also sort of known as like inductive bias. If we train a network end to end, just hand it a whole bunch of images of a scene and train it to predict new images of said scene, there's no guarantee. We can penalize it pretty heavily for warping the object between different viewpoints. We can penalize it pretty heavily because we know, like, we have ground truth views of the object from different views. We can penalize it pretty heavily if the shape is inconsistent across images generated of it. But at test time, there's no 100% bona fide way to make sure that the shape is consistent. So on the right-hand side, this was something done just sort of janking something with StyleGAN. There was no underlying three-dimensional representation at all. It's just completely deep learning end-to-end, no inductive bias. You can see the hair is changing, the nose is changing, the mouth is opening. Like, the shape is not consistent across different views. On the bottom, we have a neural radiance field of a plant, and you can see there's like almost perfect consistency across the entire thing. Well, there has to be. We've forced, by putting it through this bottleneck, by learning a neural radiance field, we've guaranteed that when we go to generate a new view, it is going to be consistent with the shape across all these different views we're generating. Does that make sense to people? This sort of motivate, like, Why? And it doesn't just apply to radiance fields. Like, why would we learn a radiance field? Why would we learn a mesh of an object? Why would we learn anything? Why bother with that if our goal is just to get new images of said object? And it boils down to wanting to make sure that this is consistent across all of our new views, that this is feasibly an object. Yeah, that's sort of the bottom line with this. And we can use anything, we can use meshes, whatever, but just radiance fields give us some nice properties and allow us to represent super fine details like this. So as someone brought up earlier, reflections are difficult. And when I said that we take in position X, Y, Z and spit out a color and a density, I was kind of lying a little bit. So if you look at a mirror from two different angles, the color on the surface of the mirror is going to be completely different. Because in real life, light reflects. And in our little toy demo where we're pretending that light just moves in a pure straight line through objects, we get completely different physics. So when I said we're taking in X, Y, Z and spitting out color and density, I was lying a little bit. What we're actually going to do is take in X, Y, Z and a viewing direction to our function to make things a little bit more complicated. So if we now take in both position, this is a vector, I should say, of angles. So now we're taking in a position in space where we're taking our image from, and also what the orientation of the camera is, which will help us when you have things like glare, as you can see in the bottom of this image. If we train a nerf without, we basically get rid of that term, the view dependence. When we get rid of view dependence, you get basically very matte looking objects. Whereas on the left-hand side, you can see there's glare from like the lighting. On the left-hand side, we learn a radiance field that feasibly, it looks like it has glare in the scene, which is much more impressive. And obviously things like mirrors would just be absolutely like impossible to learn if you don't have this view dependence term. So we're really going to take in X, Y, Z and the angle at which we're taking this photo from. Do people have questions on this? Because this is definitely a weird concept. Yeah. Okay, if you have more questions later, if you thought about it a little more. Yeah, what's up?
Do you use like the camera's gyroscopes to feed at that angle? Or again, you're not.
I mean, we're gonna assume like we have it, but you can, yeah, structured from motion is hard. I'm gonna gloss over that for right now. But yeah, that's a really good question. It's pretty non-trivial to both get the position of cameras in space when we're pre-processing all our data, our video of a camera moving throughout space. It's pretty non-trivial that we can get both the position and the orientation of the camera when we're processing our data. Yeah. Are there more questions? Okay, party on. So let's take a look inside this black box F now. This is deep learning. At the core, it's basically just an MLP. It's a pretty simple MLP. There's really only two parts to it. We'll talk about positional encoding a little bit more, but the thing I want you to take away right now is the first thing we're going to do is we're going to pass it through one multi-layer perceptron, one just basic dense neural network, and it's going to output density. And then we're going to take some intermediate activation from that multi-layer perceptron, and as well as our view dependence, which angle it's being taken from. And we're going to use that to get color. And sort of the reason we would bother passing in some of our activations from our density perceptron network into our color MLP is simply just because there's probably some similarities between them. Like if you have to answer the question like how much stuff is at this point in space, if you can learn how much stuff is at this point in space, you can probably also learn color from very similar features. Do people have questions on the basic structure of just throwing two MLPs, two multi-layer perceptrons at this to just use as our F, like a neural network? Yes.
So just to like verify.
Yeah.
The density is like independent of the two, right? Like it's like no matter where it is.
Yeah.
Like density.
Exactly. Yeah.
I think one
the point, yeah, the density here should be the same regardless of whether my camera was here or here when it was taken. So that's why we don't want this network that's predicting density. We don't want it to have access to view direction at all to guarantee that there's no way that the shape can be inconsistent from different viewpoints. Yeah.
So,
Yeah.
like, so when we screen the or we're doing the break right through the space, will a single like point in the space ever like be like 8x2 radius? Like that?
Yeah. I mean, about if we have two cameras of this dozer, one ray will probably go through this point, and another ray might not hit that exact point exactly, but it'll definitely get pretty close.
Okay, so for a single camera, we're not.
No. Yeah, unless you have some weird kind of camera that can point rays. Yeah, your camera would be wild. I'm sure you could create one using a bunch of like lenses and stuff, but yeah, it's not likely. Okay, so again, these are just MLPs. They're just dense neural networks. Very basically, the first one takes in XYZ. The second one takes in view direction, as well as some of the intermediate activations from our first neural network, just to sort of reuse some of the compute. Yeah, it's going to allow us then to account for a little bit of view dependence, but the density is not going to be changed by your view dependence, your viewing direction. So this is basically what it looks like. We're going to feed in, ignore the gamma for now. We're going to talk about that in just a second. But you're going to take in your position in space, pass it through a dense neural network. At some point, you're going to spit out at the very second to last layer. You're going to output your density, and then it's also going to take in view dependence immediately after that. And then at the very end of the network, we spit out RGB. So we output density near the end of the network, but critically before we ever take in view dependence. So it just means that we can reuse some of the computations between, having to predict density and having to predict color. So it's one MLP, but halfway through we output density, and then immediately after take in our viewing direction. But it's just a very simple hidden layer style neural network. Nothing insane going on. Yeah. So what was the gamma? What is this thing, this phi here, in between our XYZ and the input to our network? I'm only going to go over this fairly quickly so we can make sure to have lots of time to look at pretty photos and live demos and stuff. But positional encoding, what is it? It's basically a little trick. Rather than just have XYZ as an input to our network, if we learn some kind of binary representation of X, a pseudo-binary, I should say, representation of X and Y and Z, our neural network is going to be able to create very, very sharp decision boundaries. And I'm going to skip ahead to the next slide real fast. Oh, where was it? No, here it is. If we don't use positional encoding, if we pass in X, Y, and Z raw instead of first positionally encoding them with some kind of binary-ish representation, we get very blurry lines. We don't get sharp, crisp edges. As soon as we bring back in the second to right image, as soon as we bring back in positional encoding, we get really crisp boundaries. And sort of the reason in my mind for that is that neural networks are really good at learning logic gates. They can, at least. You can hard code all the weights and biases of a neural network with maybe 3 little hidden units to make an AND gate or an OR gate. If a neural network can learn a logic gate, it would be best if we can pass into them something that already looks like binary, so that we can create these very sharp. We can make use of the fact that our data is in a format that is conducive to AND gates, OR gates, whatever. That's a very high level representation. I don't want to spend too much time on this, just so that we can get to the pretty photos at the end. But feel free to come up and ask more questions about this, because I have a longer explanation I can give. Yeah, it's basically blurry or not blurry. All of these tiny little itty bitty details, sharp changes in our image, correspond to high frequency details, and just blurry things like a green blob for this dragon would correspond to like a low frequency detail. It's a weird thing. And again, I don't want to spend too much time on it just for sake of time. So feel free to come after, and I'm happy we can break it down a little bit more on the blackboard. So again, the different things we talked about on the right-hand side, we want to use positional encoding because it's going to allow us to learn very sharp boundaries between areas of this object that are extremely dense and then not dense at all. Otherwise, we get this like smearing effect. And we want view dependence because it's going to give us little effects like glare, like reflection and stuff. And that's what allows us to sort of mimic on the very left-hand side, the ground truth, where you can see the tread of this bulldozer has a lot of like glare coming off of it, which would be very difficult to learn otherwise. So that's sort of basically what a nerf is. We've gotten through most of it, so enjoy some pretty photos. On the left-hand side is a radiance field where the camera is going through a pond and then back out again in a nice pretty valley. On the right-hand side, this was at one of my research meetings where we do nerfs stuff. So we all sat still while someone walked around with the camera. And that's all of us. And you can see on the left, bottom left, why radiance fields are important. Things like fire. You can't really do it with a mesh, something that's like semi-see-through. It's very difficult. Radiance fields are really good at that. So I don't know. Pretty photos. This is why it makes me happy. So yeah. So just some minor little details. So like sampling. If we sample sort of uniformly at uniform distances all throughout our object, that's okay, but it's kind of inefficient. Most of that's just air. We can do a little bit better. So instead of just doing one round of sampling where we're just going to sample all the points uniformly, let's do 2 rounds. In the first round, we're going to sample uniformly and sort of figure out, okay, I think there's a bulldozer in this little middle region of the image. And out here on the edges, there's like nothing. Sort of get a sense of like, okay, along our array, where is there stuff and where is there not stuff? Like preliminary sampling. And then after the fact, after we've maybe done like 64, I think was the standard for the original NERF paper. After we've done like 64 uniform samples along this array, let's do 256, a lot more samples where we actually received some density, where there actually was stuff to be sampled. So it's basically just, let's sample slightly more intelligently. Let's do 2 rounds of it instead. And in practice, as just a little detail, sometimes we'll just represent the coarse round of sampling, the uniform round of sampling with a separate MLP. So we'll learn 2 separate networks with the idea that our second network that samples only around the edges can spend most of its network capacity, most of its knowledge, just learning these fine little details, and not because it takes time and effort to learn that 95% of the scene is air, and we don't want the network to waste its time doing that. We want all the crispy little details. So for our loss function, we have ground truth images taken from different points in our scene. And we know what color things should be if we look at an image taken from a specific location. We're basically just going to compare that. We're just going to do an L2 loss. Just how close was our RGB values? How close did we get? This is the loss function we're going to use. It's pretty straightforward. The only note is maybe we don't have GPUs big enough to sample every single pixel for every single image. So we're only going to render maybe like 4,000 rays or so, and just compare those 4,000 pixels and see how well they do. And as a little note, there is no direct loss on density. We train purely on how good our color is. And this is pretty non-trivial to think about. The fact that we never constrain what the density is at any point in time. We don't ever supervise the density directly. And the reason this sort of is at a very high level, again, I'm sort of rushing so we can get to the fun photos at the end and the demos. But the reason this sort of is because if you want your color to be correct along this ray, the density better be correct too. If our color out here is just noise, right? Because there's not really an object here. If our color out here is just noise and we predict really high density out at the very beginning of this ray, we're going to get just pure noise. Our predictions are going to be garbage. However, the tiny little contributions that got mostly shut out, but the tiny little contributions from out here that have, correct density, will end up contributing back positively to our loss. And our network will say, okay, at this point in space, where there actually was a bulldozer, if we had a higher density, because we have correct color out here, and we had lower density out here, where there was just garbage, we would have gotten a better prediction. I mean, at a very high level, gradient descent goes burr. Volumetric rendering is very good. Yeah, I'm gonna rush this a little bit more, but this is super non-trivial that this works. Yeah.
Generally, your render estimate of color, like that color is dependent on density, right? So it's just like another parameter that you kind of.
Yeah. I mean, our volumetric rendering function is just a bunch of additions and multiplications. If we, from this position, have a ray intersecting through our bulldozer, and from this camera, we have a ray that intersects the exact same point on our bulldozer, we're not going to get good results if we predict, that there's high density out here before this point of intersection. This point of intersection right here will have consistent color between these two, or consistent-ish color between these two views. So it'll learn like, hey, like we would have had significantly lower loss if we just listened to this color out here. It basically just boils down to, if you have enough cameras, you can sort of imagine triangulating all of these different points all along our object. Yeah.
So this is kind of a result of like a choice, right? That like you probably do not know the density at some point, right?
No, we don't. Yeah, we don't have any. Yeah, it wasn't a clever choice. It's just we don't have depth information. So that's basically it. We're going to sample uniformly. We're going to get a rough estimate of like our density, and we can train our coarse network by saying how well was its RGB, how well were the colors compared to the ground truth images. We're going to use those densities we got to sample more effectively just around the middle of our bulldozer, and pass that through a separate network that's really just good at learning these fine details just at the edge of our object. And that's what we're going to output. So that's basically it at this point. So why does this work at all? Again, we're sort of assuming we know camera positions. It boils down to, again, just if you have enough images and enough different rays that correspond to the same point on the object, the easiest way for the network to get low loss is to just output that your point in space where all these rays are intersecting on the surface of your object, just output that this has high density and output the correct color. That's like the easiest way for it to get low loss. I want to get to some nice demos here. So I have, let's see if I can pull this up. This is a project I was working on. It's not running right now, so that's why it looks like this. This was like a video my sister sent me out in like Bodega Bay. Basically just of, come here, I gotta find the command. Let's see if I can get it to run here. Of just a bench out by the beach. And I just ran it through the pre-processing script that like this library that I was working on has. It's gonna load up the data here in a second. Come here. There we go. We can see the images loading into the scene now. It's kind of hard for me to control this, sorry. It's a little bit on the slow side right now, but I'm just connecting to a server that's doing this for me. And in a second, when all of these have loaded in, we will see the scene start to render here and train in real time. Should be about done. There aren't that many more camera poses. It kind of ends about there. Come here, buddy.
That's you find the center. See like a different origin.
Yeah, you'll notice when we ran the pre-processing script, it got it kind of wrong. So these were taken vertically, but you'll notice when the data was pre-processed, it decided that the up direction was kind of to the side. Didn't quite get it right. Pre-processing is hard. So you can see it's actually starting to train here. I'm going to set it to have very high detail and be very slow. So it's not going to be training much. So it's supposed to be stairs out here, sort of on the beach. And in a minute here, we'll start to see some stairs forming in the horizontal. There we go. The original nerf took like 3 days to train. Very slow. What was that? This is using a derivative that our library came up with called Nerfacto. It's basically just an amalgam of a bunch of different nerf derivatives called like instant NGP, MIP nerf. I'll come back. So you'll notice this was taken, I didn't really give my sister any instructions for this. She just took a capture of this. It's all pointed in the same direction. There's no information. We don't have any images pointing behind us. So there's kind of a lot of fuzz right behind the images. There's a lot of noise that gets learned in all the directions, all the areas where our model, never actually saw what the scene looks like. Yeah, it's a good question. In this case, we've constrained the space just because it's a little bit hard for a network to learn good values all the way up to infinity and back. So in this case, there is a bounding box put around it, and anything outside the bounding box, we're not going to query it. Though if you want to do infinite scenes, some people do that. Yeah, so what we're using here to represent, so actually, let me see if I can turn, because it actually, you can see out onto the beach a little bit and sort of supposedly infinitely away. You can kind of see the beach a little bit there. So that's not just learning stuff at the edge of the bounding box. In this case, we actually have something called scene contraction. So instead of taking in our positionally encoded XYZ, the first thing we're going to do is we're going to warp X, Y, and Z. So instead of being out at like 100,000, we're going to apply some like continuous warping of the space so that everything is sort of kind of close. So the actual X, Y, Z and values that our network gets have been transformed a little bit and squished. We contract space down so it's close to the scene a little bit. It just means that we're not passing in values that are like 1 million. Because if a network gets a really huge value, it's probably not going to do super well with that.
Well, are you not like a single one space having it like unit
I mean, you can just put a bounding box and just say we're never going to let the network query. We're never actually going to train on any points that were queried outside of this little cube around our object. Okay. Like you can do that, but sometimes you want to represent things that are really far away. This scene isn't particularly good, so you can keep asking me questions here, and I'm going to cancel and start one that of the Campanile. That's a little bit better. Let me see, or not the Campanile, it's out in front of Doe, actually. Where is it? Okay. Let me reload this. Sorry, where were we at?
No, I was just asking like space bounded because like as you said, like
yeah, if the network gets a value that's like 100,000 times larger than a value it's ever seen before in training, it's gonna just freak out and it's not gonna do very well. So yeah, the reason we would want to take all of infinite space and sort of contract it down so that all of space sort of fits in this little box is just to make sure that our network only gets values. It only ever gets values that are, between like -1 and 1 or so. Just so it's only ever getting values on the same order of magnitude. So yeah, we apply this little math trick. So every single point in our contracted space corresponds to a point out in like our real space. There is, if this isn't loading, I'm actually going to go show you. Oh, it is loading. But this one takes a minute. There's a lot of images of this. Where is it? This is the library we're using for this. There's a really nice graphic of what it looks like. So say we have this scene. And maybe these little cone objects continue all the way out to infinity, right? If we're sampling all the way out to infinity, this Y value has to, our network has to be able to spit out good values, good colors, good densities, all the way out to infinity. That's just too much to learn. So instead, we're going to kind of contract space a little bit. So everything fits within like this little unit circle. It's just a formula that takes in any given point in space and maps it into our little unit ball, our norm ball. and it's invertible. So if we have our point in our little norm ball, we can figure out where it came from in real space. And you can do it with a cube too. Does that make kind of sense? Does that scan? This is out in Doe. Oh, I'm gonna make sure I'm on the right branch too. But I think this is working. Yeah, good. So let me up the quality here. Yeah. So this is out on Doe. So you can see the Campanile kind of up there. It's quite far away. We can actually move around. So let's kind of, we can exceed the boundaries because we're using space, or we're contracting space. We can keep going. The only problem is because we never had any training images that were out this close to the Campanile. Our network is going to get progressively worse the closer we get to it. And if we get to a point, if we kind of move a little bit to the left, you'll see it's not really learning the Campanile as much as it is learning a bunch of God rays that kind of look like the Campanile. So there's all of these sort of God ray looking things. And if we sort of back into our scene a little bit, we'll see it come back into view. But yeah. So there's lots of different fancier versions of NERFs that'll do, space contraction. So many cool advancements have been made that allow us to train this in seconds instead of days. Yeah, a lot of really cool engineering has happened. Yeah, are there more questions, comments, or concerns? Because we're definitely at the end of lecture. If people just want to come and vibe and just look at pretty pictures with me, I'm happy to do that. And there were more questions that were I didn't have enough time since I wanted to go over the recap of NERFs again. I didn't really talk about like why it's non-trivial that we can learn density. Like, why does this work at all? Because we can come and chat about that too. But I'm going to stop the recording here. Only people that come to lecture get the answers. Haha.